All right, let's talk about another type of nucleophilic addition. In this case, we're talking about the addition of alcohols to the carbonyl group that we've seen several times before. In this case, what we have is alcohol, and this could be alcohols of any carbons, 2, 3, 5 carbons, it doesn't really matter, along with the presence of a catalyst. And if you remember, the catalyst is because alcohols are not all that great nucleophiles. So what the catalyst does, it adds to the oxygen here, makes this oxygen, well, it gives it 3 bonds here and a plus charge, making this carbon more electropositive. But we'll go through that in the mechanism here in just a minute. Overall, notice we have two equivalents, two equivalents of alcohol here. And what that means is 2 alcohols are going to be adding to our carbonyl group. Not at the same time, sequentially, but over the course of the reaction, 2 of them will add. And they form this product. It's a carbon with oxygens either side of it. All right? We've seen carbon, oxygen, carbon, that's an ether. This is something called an acetal, where there's a carbon and 2 oxygens either side of it. Single bonds. All right? So this reaction is acetal formation. Now, one of the important things about this reaction and a lot of addition reactions like this is it's essentially an equilibrium. Each one of the steps is an equilibrium step, so we'll see that in the mechanism. And this actually consists of a whole bunch of steps. In the textbook, an entire page is devoted to this mechanism. So there are a bunch of steps, but they do follow chemical logic, so hopefully you can follow along, and it really isn't all that difficult. It's just a case of figuring out what's happening where and just not getting yourself lost. Okay. So this is the overall reaction. We go from a carbonyl to an acetal with a catalyst, an acid catalyst, and 2 equivalents of alcohol. So let's look at the mechanism. And remember, all these steps are all equilibrium steps. Okay, so anytime we have an oxygen and an acid, it's always going to do the same thing. The electrons on the oxygen are going to say, hey, I like you, and I'm going to go grab you. All right, so they grab the hydrogen, in this case from the HCl. And so what happens is, what we get is our protonated cyclohexane, or cyclohexanone, I should say. So I'm just going to keep everything in one color here. So what we've done is protonate that oxygen. And because of that, you will remember we have a plus charge on our carbon, which makes this carbonyl that much more reactive. So let's take our first equivalent of alcohol, because this is where this first comes into play. We have our alcohol, and that's supposed to be just a electron pair. Let me try that again. Let's see if it'll do it. I'll try a different color. Okay, there's our lone pair from our oxygen. Now, whereabouts in this molecule would those lone pairs attack? Well, they attack the same place they always do. It's at the most electrophilic part of the molecule, and it's the carbonyl carbon. So these electrons will go over here, kicking the electrons up onto the oxygen. All right. Remember, these are all equilibrium steps. So let's see what we get here. We have our 6-membered ring again. Now that doubly bonded oxygen that we originally had is now just an alcohol. But also to that carbon we have added the alcohol. We have this oxygen, which actually has the hydrogen still on it, and it also has the CH3 that was originally on it too. And because of that, what else is on this oxygen? Well, as you would imagine, it's an oxygen with 3 bonds. It's a plus charge. The oxygen is not particularly happy. Now, one of the things there is an awful lot of in a reaction like this is water. And so, what do you think the water might do at this point? I should really put the other lone pair there as well. What do you think the water might do? Well, If you thought the water might attack this hydrogen and remove that plus charge, you would be right. That's exactly what the water does do. Takes its electrons. There are no carbonyl groups for it to attack here, and water's not a very good nucleophile anyway, so it acts as a base and kicks those electrons up onto the oxygen. And what we get here is, well, we get H3O plus because we've just protonated our water, but that's not what's important. What is important is the organic product that we get. We have this alcohol here, but now we have this guy, and we've lost that hydrogen. Boy, that looks a mess, doesn't it? Anyway, that is our intermediate at this point. Now, let me just go back a slide here. Take a look at what our acetal looks like. It's a carbon with 2 oxygen groups coming off it. Okay? Now, bear that in mind, that's an acetal. What we have here is what we could consider to be the midpoint of that, of the whole reaction. We've gone halfway through. So, what's the name for half a circle? Who remembers that? Well, of course, it's a, well, yeah, what's the name for half a sphere? You would call that a hemisphere. And so, in the same vein, this is actually what's known as a hemi-acetal. All right? You're not going to find this sort of hemi inside a Ford F-250, but this is a hemi-acetal. We are halfway through our reaction, okay? And then literally all that happens is just what's happened happens again. Now, I'm going to start on a new slide, but I'm going to start with this hemi-acetal, okay? So let me just draw this hemi-acetal out. And what we'll see is, if you can do what we did on the first slide, you'll see that we're essentially just doing the same thing all over again. So here we go. Here is our hemi-acetal. All right. And we have more of our HCl. Let's say we have more of our HCl here. Okay. Let me just get rid of that naughty little thing. Okay. So, based on what we did before, what do you think is going to happen here? We have more acid in our system, and what's going to happen is exactly the same thing as happened last time. Our alcohol, or our alcohol in this case, will grab that hydrogen and break that carbon chlorine bond. Okay. Now, one of the things you might be asking is, well, that's okay for you to say that, but you know, that does raise a concern. Why couldn't this oxygen do it? Because you know what, they look both the same. Well, the fact is, this is why these are all equilibrium steps, because this could grab that hydrogen, all right? And if it did, we would go back to this, all right? So if this were to grab that hydrogen, we would go back to here. All right, so this wouldn't be something new, and then we could go back to here again. That's why all these are equilibrium steps, all right? There is nothing here that is unusual, that this reacts and this doesn't, because this one potentially could. It would just send you off in the wrong direction. That's what an equilibrium is. So, let's say the reaction is going the way we want it to, and, oh boy, excuse my crap. Not literally, but anyway. So let me draw out that cyclohexane ring again. I'm going to draw on the acetal here, or the OCH3 at least. And now, think about what we have here. We now actually have a protonated alcohol. So what are we missing on this carbon, on this oxygen, sorry? Well, we're missing what we have always had when we have an oxygen with 3 bonds, and that's plus charge. And what sort of group do we have here? And when I say what sort of a group, I mean, what could that group do? Well, the fact is, you protonate that alcohol and you go from a bad leaving group to a great leaving group. If only you had something to help kick that group out. Well, the fact is you do have something to help kick that group out in the form of this oxygen on one of its lone pairs. This oxygen can say, well, you're going to go bye-bye, so I'm going to kick these electrons into this bond, and in doing so, I'm going to kick you out. So, get out. Now let's see if we can draw out what we get out of that. Going to have to be a little bit careful. Here's our six-membered ring again. Notice now we have lost the water, and we now have a double bond to that oxygen. But we still have the methyl group there. Okay. What do we put on the oxygen when we have three bonds? Of course, it's always the plus charge. All right. Now, water could come back in here at this point and create this, but again, that's not leading us to our product. This is actually where our second equivalent of alcohol comes into play. So I'm going to draw that out here, CH3OH. And so my question to you guys is, just as it was last time, where exactly is the alcohol going to add in this step? Well, the fact is it's no different to where it added last time. Yeah, the functional group looks a little bit different, but it's always going to be the most electropositive part of the molecule, the carbonyl carbon. And that's exactly what happens. So that goes up here, kicks the electrons up onto that oxygen. Okay. And so what we get here is, once again, we have our six-membered ring, so let's draw that on. There's our six-membered ring. So now we have the OCH3. Notice we have that part of our acetal back again. And now what we have is our O, we have another CH3, but what else is on that oxygen? Well, it's the hydrogen. And once again, blah, blah, blah. What do we have on an oxygen that's got three bonds to it? Of course, it's a plus charge. Okay, you know what? Let me put that in a place where it's a little more clear about where it actually is. So that plus charge is on this oxygen. All right. Now, bear in mind, up here, we lost some water. That water's going to come back into play here. All right, and it's going to say, hey, look at me, I've got some electrons, and you don't. Therefore, I want something you have. This oxygen wants to remove its plus charge. This guy has a bunch of lone pairs, so you can imagine what's going to happen. The oxygen says, hey, I'm going to take my electrons, grab that hydrogen, break that bond, put those electrons onto that oxygen, and we're going to get, this is actually the final structure here, this is our final product. Bingo. We did actually get there. We have one OCH3, and now we have two OCH3s. This is our acetal. Phew, that's quite a few steps to get there, but I'm hoping that you can see there is a pattern that we're following. The pattern that we follow in our first three steps is essentially what happens in our last four steps. Okay? It really is very similar. So, although it's a relatively complicated reaction with several steps, I hope you can see it's really not hugely difficult in terms of following the electrons. Okay? At least I hope that's what you think. Anyway, that's the reaction for nucleophilic addition of alcohols to form acetals. Thank you.